seeds than another which, in equal time, has absorbed less of them. We consequently observe, in a hot summer, when a further supply of mineral ingredients from the soil ceases through want of water, that the height and strength of plants, as well as the development of their seeds, are in direct proportion to its absorption of the elementary parts of the soil in the preceding epochs of its growth. The fertility of the year depends in general upon the temperature and the moisture or dryness of the spring. If all the conditions necessary to the assimilation of the atmospheric nourishment be secured to our cultivated plants, the action of humus then, as we have explained it above, is chiefly of value in gaining time. In agriculture this must ever be taken into account, and in this respect humus is of importance in favouring the growth of vegetables, cabbages, etc. But the cerealia and plants grown for their roots meet on our fields in the remains of the preceding crop with a quantity of decaying vegetable substances corresponding to their contents of mineral nutriment from the soil, and consequently with a quantity of carbonic acid adequate to their accelerated development in the spring. A further supply of carbonic acid, therefore, would be quite useless without a corresponding increase of mineral ingredients. From a morgen of good meadow land, 2,500 pounds weight of hay, according to the best agriculturists, are obtained on an average. This amount is furnished without any supply of organic substances, without manure containing carbon or nitrogen, by irrigation and the application of ashes or gypsum. Double that amount may be grown, but assuming 2,500 pounds weight of hay to be the maximum, we may calculate the amount of carbon and nitrogen derived from the atmosphere by the plants of the meadow. According to elementary analysis, hay, dried at a temperature of 100 degrees Reaumur, contains 45.8% of carbon and 1.5% of nitrogen. 14% of water retained by the hay, dried at common temperatures, is driven off at 100 degrees. 2,500 pounds weight of hay, therefore, corresponds to 2,150 pounds dried at 100 degrees. This shows us that 984 pounds of carbon and 32.2 pounds weight of nitrogen have been obtained in the produce of 1 morgen of meadowland. Suppose that this nitrogen has been absorbed by the plants in the form of ammonia. The atmosphere contains 39.1 pounds weight of ammonia to every 3,640 pounds weight of carbonic acid, equals 984 carbon, or 27%. Or in other words, to every 1,000 pounds weight of carbonic acid, 10.7 pounds of ammonia, that is, to about 1/100,000th the weight of the air, or 1/60,000th of its volume. For every 100 parts of carbonic acid absorbed by the surface of the leaves, the plant receives from the atmosphere somewhat more than 1 part of ammonia. With every 1,000 pounds of carbon we obtain from a meadow 32/7 pounds of nitrogen from cultivated fields in wheat, 21.5 pounds of nitrogen, oats 22.3 pounds of nitrogen, rye 15.2 pounds of nitrogen, potatoes 34.1 pounds of nitrogen, beetroot 39.1 pounds of nitrogen, clover 44 pounds of nitrogen, peas 62 pounds of nitrogen. Bossingalt obtained from his farm at Bechelbronn in Alsace in 5 years the shape of potatoes, wheat, clover, turnips, and oats, 8,383 of carbon and 250.7 nitrogen. In the following 5 years, as beetroot, wheat, clover, turnips, oats, and rye, 8,192 of carbon and 284.2 of nitrogen. In a further course of 6 years, potatoes, wheat, clover, turnips, peas, and rye, 10,949 of carbon, 356.6 of nitrogen. In 16 years, 27,424 carbon, 858 and one half nitrogen, which gives us for every 1,000 carbon 31.3 nitrogen. From these interesting and unquestionable facts, we may deduce some conclusions of the highest importance in their application to agriculture. 1. We observe that the relative proportions of carbon and nitrogen stand in a field relation to the surface of the leaves. Those plants in which all the nitrogen may be said to be concentrated in the seeds, as in cerealia, contain on the whole less nitrogen than the leguminous plants, peas, and clover. 2. The produce of nitrogen on a meadow which receives no nitrogenized manure is greater than that of a field of wheat which has been manured. 3. The produce of nitrogen in clover and peas, which agriculturists will acknowledge require no nitrogenized manure, is far greater than that of a potato or turnip field, which is abundantly supplied with such manures. Lastly, and this is the most curious deduction to be derived from the above facts, if we plant potatoes, wheat, turnips, peas, and clover, plants containing potash, lime, and silex, upon the same land, 3 times manured, we gain in 16 years, for a given quantity of carbon, the same proportion of nitrogen which we receive from a meadow which has received no nitrogenized manure. On a morgen of meadow land we obtain in plants containing silex, lime, and potash, 984 carbon, 32.2 nitrogen. On a morgen of cultivated land, in an average of 16 years, the plants containing the same mineral elements, silex, lime, and potash, 857 carbon, 26.8 nitrogen. If we add the carbon and nitrogen of the leaves of the beetroot and the stalk and leaves of the potato, which have not been taken into account, it still remains evident that the cultivated fields, notwithstanding the supply of carbonaceous and nitrogenized manures, produce no more carbon and nitrogen than an equal surface of meadowland supplied only with mineral elements. What then is the rationale of the effect of manure, of the solid and fluid excrements of animals? This question can now be satisfactorily answered. That effect is the restoration of the elementary constituents of the soil which have been gradually drawn up from it in the shape of grain and cattle. If the land I am speaking of had not been manured during those 16 years, not more than 1/2 or perhaps than 1/3 part of the carbon and nitrogen would have been produced. We owe it to the animal excrements that it equaled in production the meadow land, and thus because they restored the mineral ingredients of the soil removed from the crops. All that the supply of manure accomplished was to prevent the land from becoming poorer in these than the meadow, which produces 2,500 pounds of hay. We withdraw from the meadow in this way hay as large an amount of mineral substances as we do in one harvest of grain, and we know that the fertility of the meadow is just as dependent upon the restoration of these ingredients to its soil as the cultivated land is upon manures. 2 meadows of equal surface, containing unequal quantities of inorganic elements of nourishment, other conditions being equal, are very unequally fertile. That which possesses most, furnished most hay. If we do not restore to a meadow the withdrawn elements, its fertility decreases, but its fertility remains unimpaired when a due supply of animal excrements, fluid and solid, and it not only remains the same, but may be increased by a supply of mineral substances alone, such as remain after the combustion of lignaceous plants and other vegetables, namely ashes. Ashes represent the whole nourishment which vegetables receive from the soil. By furnishing them in sufficient quantities to our meadows, we give the plants growing on them the power